in part of my work, I'm working on mucus permeating SMEDDS containing thiolated compounds. First, I would like to give you a brief introduction to the topic, then I will introduce you the SMEDDS formulation I work with and end up with recent results. So, the mucus barrier covers various body cavities, such as, for example, the gastrointestinal tract. The mucus is a kind of protection for the underlying epithelial cells because it hinders foreign particulates, like, for example, pathogens, to reach the underlying epithelium. So, the mucus is constantly secreted and renewed. So, when particles are once stuck into the mucus, they will be removed. This mechanism is also a challenge for us when we try to formulate novel formulations, because drugs have somehow to need to permeate this mucus layer. The mucus barrier consists of negatively charged glycoproteins that have distinguished subunits that are connected by disulfide bonds. So we have, first of all, this mucus barrier that has to be overcome, and there are other aspects that we need to take in consideration when we try to formulate proper drug formulations. There is an important issue for poorly soluble drugs. This is the dissolution step. An important strategy to come these dissolution steps are SMEDDS. They enable poorly soluble drugs to be properly dissolved by forming these self-microemulsifying drug delivery systems. These are microemulsions that have the capacity to form spontaneously when they are brought into aqueous solution, like for example gastric juices. These microemulsions are thermodynamically stable, and due to their large surface, they have a high dissolution velocity. This brings me to the aim of my study. These are SMEDDS that have the capacity to permeate the mucus. This could be achieved by firstly synthesizing thiolated emulsifiers that were incorporated into the SMEDDS and then evaluated for the mucus permeating properties. The formulation I worked with consisted of Capmol MCM, Primo4EL, Captex 355, and propyl glycol as co-solvent. In this formulation, thiolated conjugates were incorporated in. First of all, I synthesized the thiolbutylamidine dodecylamine and a further fatty acid derivative, the thioglycolic acid octylamine. Additionally, I incorporated N-acetylcysteine into another formulation. Out of these SMEDDS pre-concentrates, the SMEDDS were prepared by using Mr. sulfur of pH 6 in a 1:100 dilution step. The formed SMEDDS were then characterized for size and zeta potential using the dynamic light scattering technique, and for their effective diffusion coefficient in mucus by using multiple particle tracking. Multiple particle tracking is a technique that allows us to observe particle movement within a matrix, like for example, porcine mucus in my case. With this technique we can allow the particle movement of several hundred particles. So, to study the particles movement within a matrix, the particles are initially labeled using a fluorescent dye. Then the samples are inoculated with our matrix, in this case porcine mucus, and are observed by using microscopy, and afterwards the data can be analyzed. With this dynamic measurement, more than 100 particles for each formulation can be observed within one measurement cycle, and what we finally measure is the mean square displacement out of which we can calculate the effective diffusion coefficient. Let's come to the results. The plot shows the particle diameter against or versus the effective diffusion coefficient. We could reach particles for all formulations indicated with SMEDDS TBAD, SMEDDS Na6, SMEDDS TGAO, and SMEDDS C. All formulations were in a very narrow particle range of 50 nanometer, which is good, as the mucus mesh per size is reported to be 100 nanometer. So we are still below for all formulations. Regarding the effective diffusion coefficient, we could see that all thiolated compounds had beneficial effect because they increased the effective diffusion coefficient. Especially in case of the thiobutylamididodecylamine, we could increase the effective diffusion coefficient in mucus up to 87-fold in comparison to the original SMEDDS formulation. N-acetylcysteamine led to an improvement of 24-fold, while thiobutylamidodecylamine led to a 5-fold increase. We can conclude that there seems to be no significant relationship between size and effective diffusion coefficient in mucus within this particle size range. So obviously there is no steric obstruction of the particles in mucus. Regarding the charge of this particle's surface, we could detect for all four formulations a theta potential around 0 millivolt or slightly negatively charged, which is favorable for particle to pass to the negatively charged mucus. So we can conclude there is no significant relationship for the theta potential and the effective diffusion coefficient in mucus. So there seems to be no ionic or steric interaction of particles in the mucus. Here we analyze the effective diffusion coefficient of each single particle within all four formulations. Each single effective diffusion coefficient was then ranked for all particles within one formulation, ending up with shown in this plot with the lowest effective diffusion coefficient on top and the fastest on the bottom. We could here see, if we regard the subclasses, how the particle movement is homogeneous or heterogeneous, that the thiolated compounds could show an increase in homogeneity. If we regard the fastest and the slowest percentile, in case of the thiobutylamidine, we had only a difference of 21 times in comparison to the original formulation indicated with SMEDDS C, that is a difference of more than 1,000 times. The other two thiol compounds, thiobutyl acetylactylamine as well as N-acetylcysteine, could further improve the formulation to only a difference of 48 times and 100 times. So we can conclude the thiolated compounds increase the homogeneity of the whole particle's movement and not only single effective diffusion coefficient. This leads us to the conclusion it was possible to successfully thiolate dodecylamine and dotylamine. It was possible to design a SMEDDS formulation that has mucus permeating properties. The formulation could increase mucus permeating properties by incorporating the thiolated compound, and also the homogeneity of particles' movement could be increased. So the known formulation could be an interesting drug delivery to overcome the mucus barrier. Thank you for your attention.
Thank you, Julia, for a very nice presentation, and it's open for discussion. Questions, remarks?
Yes, please.
Yes.
Thank you. This is a very elegant presentation, very nice. Our students in Egypt, they ask us, why are microemulsions not called nanoemulsions? What do you think? They are 50 nanometers. Why does the literature call them micro?
Yes, this is a good point. And if you try to search their literature, you find very different opinions, very interesting discussions about this point, because actually both the microemulsions as well as the nanoemulsions, they are in a nanometer range. They can vary from 50 nanometer to 300 nanometer, depending on the definition. You have to look at the system more in detail, more in terms of, is it thermodynamically stable or is it only kinetically stable? Is it self-emulsifying or not? Is the microemulsions are somehow by definition self-emulsifying. So you asked for my opinion on this point. I think it is simply coming from history that it's an historical point aspect. We had the emulsions, then we had the microemulsions, and then there appeared somehow other formulations, because the microemulsions were there already in the nano range, and this new formulation came then up in the nano time. That's why they were called nano emulsions. But it's often very, very difficult to distinguish them.
Thank you very much. Thank you.
Welcome.
Another question?
What about toxicity?
Excuse me?
Toxicity.
Cytotoxicity. This is always a very important issue. We are trying to figure out how we will go in this topic. You have to keep in consideration, we use them in a 1 to 100 dilution, and even when you will then apply into the gastrointestinal tract, you will have there a quite high dissolution step. This is a difficult topic.
Okay, thank you. Thanks to Julia once again. Let me invite the next speaker, is Alessandra Partenhauser.